Hi, Physics 11s. This is Miss Moore, and today we're going to continue learning about uniform motion, but more on the graphing side of things. So you've taken a look at your warm-up question. You may have noticed it's the same question from assignment 3 from yesterday, and the reason why I put this as your warm-up is because I was wondering if you still had lingering questions about this one or why it was the case. So when we're asked which graphs model uniform motion, we're looking for which graph has a constant velocity or a graph where delta d over delta t is constant, which means the displacement changes at a constant rate per unit time. The only graph where the displacement is changing at a constant rate per unit time is graph B. Here in graph A, the change in displacement is actually zero. There is no change happening. What's physically occurring is that there is an object at a location in space that's not the origin, and it's stationary there as time passes. Here, the object is moving away from the origin or the reference point at a constant rate per unit time. And here it's actually not constant. The displacement of the object with reference to the origin is not changing at a constant rate. This is better described as an exponential graph. So this is not constant the way that this linear graph is here. So the answer is B. When it comes to graphing uniform motion, there are relationships between three different very important graphs. We have our position time graph, our velocity time graph, and our acceleration time graph. All three of these graphs can be used to describe the motion of a single object with respect to time, and today we're going to be looking at how to draw them and how they're related. So let's start with the first type, which is the position time graph, sometimes referred to as a displacement time graph. These graphs will look just like the ones from your warm-up question. It is a graph of the object's position as a function of time, and the slope of this graph is the average velocity of the object in motion. So let's draw one here, just a generic one. Pull out your ruler to help you. So we'll just choose an object that departs from the direction negative to the reference point and then travels through the reference point and travels onwards into the positive direction here. We'll call this point here D1, or the initial position of the object, and then this point up here, we'll call it D2, or the final position of the object. The slope of this graph is defined as the rise over the run. Rise referring to the change vertically that takes place, and run referring to the change horizontally that takes place. So in this case, the rise is going to be our change in position, and the run is going to be our change in time. So we can say that this is D2 minus D1 over T2 minus T1. Now the reason why the slope of this graph gives us the average velocity of the object is because you'll notice that change in position over change in time is also the definition of velocity. Velocity is defined as delta d over delta t. And this is why the slope gives us the velocity. I'm going to also label this on our graph so that we can clearly see the rise and the run. Okay, here's our rise or our change in position, and here's our run, oops, or our change in time. That should definitely not have a vector hat, so I'm going to take that off. Okay. So this object is experiencing a positive change in position over time. It's moving towards the origin and then through the origin or the reference point and then past it in the positive direction. So if we were going to translate this to a velocity time graph, it's going to look a little bit different, but I'm hoping that we'll see the relationship there. The velocity time graph is what shows the object's velocity as a function of time. And the slope of this graph is actually the acceleration of the object. And I'll show you why mathematically in a moment. What's also interesting is that the area under a velocity time graph gives us the displacement of that object. So we're going to draw another graph here that represents the velocity of our object with respect to time. So if we were going to translate the motion taking place here into a velocity time graph, we've observed that the change in displacement per unit time is positive and it is constant. So what does that look like on a velocity time graph? A constant, positive, average velocity, where the slope of this graph is the change in velocity divided by the change in time, or v2 minus v1 over t2 minus t1. This hopefully looks familiar because it looks just like our acceleration formula. Acceleration is also defined as the change in velocity per unit time, which is why the slope of this graph is the acceleration of the object. The area under the curve is going to be given using the same method that you would to find the area of this, imagining that it's a rectangle, which it is. So the area would be the change in velocity multiplied by the change in time, or the height of the rectangle multiplied by its length. Velocity times change in time. And because velocity is defined as change in position per unit time, if you multiply each side of this equation by delta t, you get v times delta t equals delta d, which is what you have right here. And this is why the area under the curve is equivalent to the displacement of the object. So I'm going to label that on here. The other things I'll label on our graph just for clarification is that this would be T2 and this would be T1, and actually there is no change in the velocity with respect to time on this graph because our initial velocity is some positive value here and our final velocity is that same value. So we have a constant graph here. Now how would we translate this to an acceleration time graph? If we were to graph the acceleration per unit time, we're showing the acceleration as a function of time, and in this case, the area under the curve is going to represent the change in velocity of the object. So what would this look like for our object? Acceleration is defined as the change in velocity per unit time. The velocity is not changing here, it's constant. So our acceleration is 0. We can represent that just by drawing a line along the x-axis, like so. So the acceleration is 0 because there is no change in velocity. The area under this curve represents the change in velocity, and this is because acceleration is defined as change in velocity per unit time. If you multiply each side of the equation by delta t, you will have a times delta t equals delta v. So the area under the curve would be obtained by, if this was a rectangle, multiplying the length by the height. We don't have any height because our acceleration is 0, but there will be times later in the unit when the acceleration is not 0, where you will have a rectangular shape here, and you can multiply the length, which is the time, by the height, which is the acceleration, and you will get the change in velocity experienced by your object. Let's look at an example to put these ideas together. While driving west along a flat stretch of highway from Montreal to Toronto, you set your vehicle's cruise control to the speed limit. The following data set was obtained by tracking your position with respect to the reference point, which is Montreal. The first thing we're supposed to do is draw a position time graph. We have time and position. These are not SI units, but we won't bother converting them. That's okay, we don't need to unless the question asks us to. So we're going to draw a position versus time graph here. Time always goes on the x-axis because it's our independent variable, and we only have positive position values, so we don't need to leave space for a negative component of the y-axis. So I'm just going to put my time axis here, measured in hours. And my position axis here, measured in kilometers. Okay, go ahead and plot your data points. Now that you've plotted your data points, we need to connect the data with a line of best fit. So remember from our last lesson, we learned to draw a line of best fit by drawing a line through our data points, such as our line passes through as many data points as possible, and if that's not possible, we try and get it balanced so that at least the data points are equally distributed on either side of the line. So I'm going to draw my line like this. Next it says, what is the slope of your position time graph? Recall that slope is our rise over run, or our change in displacement divided by change in time, or d2 minus d1 over t2 minus t1. Okay, so we're going to go final minus initial position, which is 390 minus 0 divided by final time minus initial time, 4 minus 0, which is 97.5 or 98 kilometers per hour. What physical quantity does the slope of your position time graph represent? Notice that our slope, since it is defined as delta d over delta t, represents the velocity of the object. What speed is the vehicle traveling at? What is the vehicle's average velocity? Now we know that speed is meant to be the distance traveled per unit time, and that's not the same as the position of the vehicle relative to the reference point per unit time. So technically we would have to know how much ground the vehicle has covered as it's going from Montreal to Toronto. So you can look that up on Google Maps on your phone. Okay. If you were driving from Montreal to Toronto, you would have covered 542 kilometers. So your speed, V, equals distance traveled per unit time, which is 542 kilometers, and you did it in 4 hours. We can calculate this. 135.5 kilometers per hour. If we were paying close attention to significant figures, we would know that we were to do our answer to one significant figure, but that's okay. Let's just leave it with 3 significant figures for the purpose of comparison to the average velocity, so we can say 136 kilometers per hour, and our average velocity, or V average, is defined by change in position over change in time. This is going to be exactly what we calculated for our slope, 98 kilometers per hour. What type of motion is this? Well, it is uniform motion, and the reason why is because the position is changing at a constant rate per unit time. You can say the change in velocity is 0, or you can say change in position over change in time is constant. You can see visually that that change is constant because this line increases at a constant rate per unit time. Okay, please try part B of this example. You're taking this data and you're translating it into a velocity time graph. The one thing I will say before you get started is that we're going to assume our frame of reference begins when the car is already in motion, traveling at a velocity of 100 kilometers per hour. So that computation is done for you. You can fill in the rest of the table yourself by calculating the values for your velocity column, and then we're going through all the graphing and analysis steps that we did in part A. So give this a try, and I will check in with you in a few moments. Okay, so I have plotted my data points and I have my line of best fit. I changed my y-axis values on this graph compared to how we plotted this one, just because I wanted to be a little bit more zoomed in and see those fluctuations in velocity. There's a little bit of fluctuation, but just kind of plop your line of best fit in the middle as best you can. So what is the area under this velocity time graph? You can figure that out by creating a sort of rectangle for yourself. So that's going to be the area under the curve. The area is the length times the width. Our length is time, and our width is velocity. So what we'll do, since we are solving a uniform motion problem, even though our experimental data is a little bit all over, we're going to assume a constant velocity here using our line of best fit to estimate, and I'm going to just say it's around 100 kilometers per hour. So in 4 hours. We're working with 100 kilometers per hour as our average velocity. So the area under the curve is 400 kilometers. What physical quantity does the area under the curve represent? It represents your displacement. Velocity equals displacement over time. Therefore, displacement equals velocity times time, which is exactly what we had up here. So this is 400 kilometers, and it represents the displacement of the car. And finally, what's the total distance traveled on this road trip from Montreal to Toronto? We did look that up in the previous question when we were on Google Maps. The total distance in terms of ground covered is 542 kilometers. What is the displacement of the vehicle once it reaches Toronto? The displacement, or the change in position, is 390 kilometers. So that's the physical straight line distance if you drew it between the two cities, and that's the amount of road covered by the vehicle. Okay, great job, you guys. Please work on assignment 4. Check your solutions on the website when you're finished and hand in your assignment. If you have any questions, please ask. I look forward to seeing you soon. Bye for now.